The greatest integer function. Hello everyone. In this subsection, we are going to explore the concept of continuity by examining a very specific and interesting mathematical tool known as the greatest integer function. Now, this function is particularly important because it serves as a classic example in calculus. It allows us to demonstrate a crucial concept, that a function can be defined for every single real number on the number line, and yet it can still be discontinuous at specific points. As we move through the next few slides, we will first define how this function works, and then analyze exactly where these breaks in continuity occur. Understanding the greatest integer function. Now that we have introduced the concept, let us dive into the formal definition of the greatest integer function. We denote this function as f of x equals x enclosed in square brackets. By definition, it represents the greatest integer that is less than or equal to the real number x. To put this in simpler terms, you can think of it as rounding down any given number to the nearest integer that does not exceed the original value. Let us look at a few examples to make this clear. First, if x equals 2.7, then the greatest integer function of 2.7 is 2, because 2 is the largest integer that is less than or equal to 2.7. Next, consider a case where x is already an integer, such as 5. In this instance, the greatest integer function of 5 is simply 5, since 5 is the largest integer that satisfies the condition of being less than or equal to 5. Finally, let us look at a negative value, which is a point where many students often encounter difficulty. If x equals negative 1.2, the greatest integer function of negative 1.2 is negative 2. This is because negative 2 is the largest integer that is less than or equal to negative 1.2. It is important to note that negative 1 is actually greater than negative 1.2, so we must move to the left on the number line to find the correct value. Understanding these specific values is crucial, as this rounding down behavior is exactly what creates the jumps in the function that we will explore through a real-world analogy and limit analysis in the upcoming slides. Real-world analogy, age calculation. Now that we have established the mathematical definition and seen a few examples, let us look at a practical way to visualize the greatest integer function using a real-world analogy, how we typically describe a person's age. Think about it this way. If a person is 17 years and 11 months old, we do not say they are almost 18. We still say they are 17 years old. They do not officially become 18 until the exact moment of their birthday. In mathematical terms, if we let x represent time, then for any value of x between 17 and 18, the age function remains constant at 17. However, the very instant x reaches 18, the value jumps immediately from 17 to 18. This sudden jump is the essence of discontinuity. As we will explore in the upcoming slides, this is precisely why the function is continuous at most points, but breaks at every single integer. Continuity at non-integer points. Now that we have established the basic definition of the greatest integer function and used the age analogy to visualize those jumps, let us examine where the function is actually smooth and continuous. Let us consider a point, which we will call C, that is not an integer. For our example, let's use 2.5. To determine if the function is continuous here, we will perform a step-by-step analysis. First, let's find the function value. When x equals 2.5, the greatest integer function of 2.5 is 2, because 2 is the largest integer that is less than or equal to 2.5. Second, let's look at the behavior of the function in the immediate vicinity of this point. If we take a very small value, referred to in calculus as epsilon, for instance, 0.1, we can see that any number between 2.4 and 2.6 will still have a greatest integer value of 2. Third, we evaluate the limit. Since the function value remains constant at 2 within this small neighborhood around 2.5, the limit as x approaches 2.5 is simply 2. Fourth, we reach our conclusion. For a function to be continuous, the limit must equal the function value. Because the limit as x approaches 2.5 is equal to the function value of 2, the function is continuous at x equals 2.5. This logic is not unique to 2.5. It applies to every real number that is not an integer. Therefore, we can conclude that the greatest integer function is continuous at all non-integer points. In the next slide, we will contrast this by analyzing what happens when we approach an actual integer. Continuity at integer points. Now that we have established that the function is continuous at all non-integer points, let us analyze what happens at a point where the value is an integer. For this example, let us use the integer 3. To determine if the function is continuous here, we must examine both the left-hand limit and the right-hand limit. Starting with step 1, let us find the right-hand limit. As x approaches 3 from the right, it takes on values that are slightly greater than 3, such as 3.1, 3.01, or 3.001. For all of these values, the greatest integer less than or equal to x is exactly 3. Therefore, the limit of f of x as x approaches 3 from the right is 3. Now, let us move to step 2 and find the left-hand limit. As x approaches 3 from the left, it takes on values slightly less than 3, such as 2.9, 2.99, or 2.999. Recalling our definition from the previous slides, the greatest integer less than or equal to these values is 2. Consequently, the limit of f of x as x approaches 3 from the left is 2. In step 3, we compare these two limits. We can see that the limit from the left is 2, while the limit from the right is 3. Because the left-hand limit does not equal the right-hand limit, the overall limit of f of x as x approaches 3 does not exist. This brings us to step 4, our final conclusion. For a function to be continuous at a specific point, the limit must exist and be equal to the function's value at that point. Since the limit does not exist at x equals 3, the function f of x equals the greatest integer of x is discontinuous at x equals 3. To generalize this for any integer c, the limit as x approaches c from the right will always be c, but the limit as x approaches c from the left will always be c minus 1. Since c can never equal c minus 1, we can conclude that the function is discontinuous at every single integer point. Key takeaways. Now that we have analyzed both the non-integer and integer points, let us summarize the key takeaways to ensure you have a clear understanding of the greatest integer function. First, as a reminder of our starting point, the greatest integer function, denoted as f of x equals x in brackets, always returns the largest integer that is less than or equal to x. Think of this as the rounding down rule we discussed at the beginning. Secondly, based on our step-by-step analysis of points like 2.5, we can conclude that the function is continuous at all points x that belong to the set of real numbers excluding integers. Simply put, the function is continuous at all non-integer points. Thirdly, in contrast, the function is discontinuous at all points x that are members of the set of integers. These are the specific points where the jumps occur, much like the age analogy we explored. Finally, it is important to remember why this happens. The discontinuity at these integer points is caused by the fact that the left-hand limit and the right-hand limit do not coincide. Because the function approaches two different values from the left and the right, the limit does not exist, and continuity is broken. With these core concepts in mind, let us move on to the final slide, where we will discuss some common mistakes to avoid when applying these rules. Common mistakes. Now that we have covered the theory and the proofs, let us conclude by discussing some common mistakes students often make when dealing with the greatest integer function, so you can avoid them in your exams. First, be careful not to confuse standard rounding with the greatest integer function. A common error is thinking that the greatest integer of negative 1.2 should be negative 1, simply because it is the closest integer. However, as we discussed in our examples, the greatest integer function always moves to the left on the number line. Since negative 2 is to the left of negative 1.2, The correct value is -2. Second, do not fall into the trap of assuming that if a function is defined for all x, it must be continuous. As we mentioned at the start of this lesson, the greatest integer function is indeed defined for every single real number, yet it is still discontinuous at every integer. Remember, continuity requires more than just a definition. It requires the limit to exist and to match the function's value at that specific point. Finally, avoid ignoring the difference between the left-hand limit and the right-hand limit. Some students might see that the function of 3 equals 3 and automatically assume the limit is also 3. But, as we demonstrated in our step-by-step analysis of integer points, you must always check both sides. For piecewise or step functions like this one, the left-hand limit and right-hand limit often differ, and it is this exact discrepancy that creates the discontinuity.